In this video, we're going to cover Kepler's 3 laws of planetary motion. And at the end, you'll also learn about Tycho Brahe and how he ended up with a brass nose. But first, Kepler's first law states that planets orbit in the shape of an ellipse with the sun at one focus. So what is an ellipse? So an ellipse is like a circle that's been smushed. So that's what the shape of an orbit, planetary orbit, looks like. And if you notice inside this ellipse are these 2 points. Each point is called a focus. The 2 points are called foci for plural. The distance from one focus to the planet to the other focus is constant. So d1 plus d2 is constant as you go around the ellipse. Also, at one focus point, you have the sun. The sun is located at one focus point, and we can measure how eccentric or how ovalish this shape is, and we call that eccentricity. So to measure how elliptical it is or eccentric it is, we take the distance between the foci, so that's the distance between these 2 points represented by the blue arrow, blue double arrow, divided by the length of the major axis. So the length of the major axis is the longest diameter of the ellipse, so which is from here to here. And the eccentricity can be between 0 and 1. 0 would be a perfect circle. 1 would be a parabola, but it wouldn't be a closed orbit. So for it to have a closed orbit ellipse, it would have to be between 0 and 1. Kepler's second law states that a planet sweeps out the same area in the same amount of time. And here we have a diagram of an orbit. And let's say that the planet were right here. And as it orbits from here to here, notice it sweeps out this area. And then as it goes to the other side, it's going to sweep out a longer distance, but the same area. Notice that this distance is longer, but the area is the same. And that's because it's not as wide. Over here, it's much wider. Here's not as wide, but then it's a little bit taller. But the area is the same. So what Kepler is saying is that if this area and this area are the same, it'll take the same amount of time to sweep through that area. And so the t is going to be the same. The d will be different because this is a smaller distance. This is a bigger distance. And so a bigger d divided by t will give you a bigger speed than a little d over t, which is a smaller speed. So what this is, the implication of this is that the further away you are from the sun, the slower the planet is moving. The closer the planet is to the sun, the faster it will be orbiting. Kepler's third law states that planet's orbital period is proportional to the average distance from the sun. The orbital period is the time to make one complete orbit. And what this law is saying is that as you are getting further away from the sun, it's going to take you longer to go around. And that relationship is the period squared is proportional to the r cubed. So r is the average distance from the sun. And next, we're going to derive this equation. Derive Kepler's third law, we're going to start with the centripetal force equation. And here we have a diagram. Here we have the sun, we have the planet. This is a circular motion. Although it is elliptical, our derivation, once we derive it, will also apply to ellipses as well. We know that between any 2 masses, there's a gravitational force. So what is playing the role of the centripetal force here is the gravitational force. And the equation for gravitational force between 2 masses is big G, which is the gravitational constant, times the mass, the product of the 2 masses. The big M is going to be the mass of the sun. Little m will be the mass of the planet, divided by r squared. R is going to be the distance between the sun and the planet, or the radius of the orbit. And that's equal to mv squared over r. Notice that the m cancels out, and one of the r's cancels out, and that leaves us with v squared equals big G times big M over r. And this big M, remember, is the mass of the sun, or the central body, whatever the large mass is. Now we're going to substitute v equals 2 pi r over t. Big T is the period. And this equation is just from speed is distance over time. The distance of a circle is the circumference, 2 pi r, and the t is the period, time to make one complete circle. So we're going to plug that into v. And on the right-hand side, we end up with 4 pi squared r squared over big T squared, the period squared. And then we're going to move the t squared to the left, and then also move the r's to the left and move everything else to the right. And we end up with t squared over r cubed equals to 4 pi squared divided by gm. And notice that this side, the right side of the equation, is a constant, which means that the period squared is proportional to the r cubed. And just a reminder that m is either the sun or some other central body, some large mass, and r is the average orbital distance. In the case of an ellipse, it would be the semi-major axis. Now I'd like to share with you one of my favorite stories in the history of science, which is about Tycho Brahe. Tycho Brahe was a Danish astronomer who collected a lot of very accurate data that Kepler was later able to use to derive his three laws. Now, the interesting thing about Tycho Brahe is that one time he had a very heated dispute with another Danish nobleman, and as a result of their dispute, they ended up having a duel. And in the duel, which took place in darkness, Tycho had part of his nose chopped off. And as a result, the rest of his life, he had to go about with a prosthetic nose. Possibly it was a brass nose. And you might wonder, what kind of argument did they have that would lead him to want to fight someone, to have a duel with someone to resolve this argument? And it ended up being a very petty argument, possibly over a mathematical disagreement, or who was more skilled in astronomy or philosophy. So that's my favorite story. Such a really petty argument, but ending up with a lost nose, and also what a really interesting guy who was able to collect such good data that Kepler was able to use to derive his three laws.